covering for this lecture, or we're going to be covering two topics, something called impedance flow, and power transformation. These are just kind of, these are, how should I put it? These concepts like load impedance, the characteristic impedance, these kind of things are actual specifications. Impedance flow and power transformation are kind of like given names, things like that. You only see it, at least in my experience, is as a lead-in to these both topics, or lead-ins to something called the Smith chart. And this Smith chart is something, I don't know if some of you may have heard about. It's very, very popular tool, important tool in uh, in transmission line, radio frequency, microwave design, as a way to look at uh, how impedances change as a function of frequency in your design. So these are lead-ins to that lecture, which will be coming in a couple, maybe one or two lectures from now. So these are just both leads in. So let's look at these things. So the first question is, um, one question is that in general, we have V0 plus, so that's a voltage waveform going from left to right, and then we have a V0 minus going from right to left in our transmission line. In T line, so and the characteristic impedance. Impedance Z0. Question is, will power be dissipated in the transmission line? Dissipated in T line as a general question. Well, in the answer is that in general, no power is dissipated in a T line that's lossless. But what does happen is that in the case where we don't have perfect matching between the characteristic impedance and the load impedance and the source impedance, etc., that there is voltage and current, and therefore power going back and potentially going back and forth um, in the transmission line as you get reflections back and forth. But eventually, possibly after many reflections back and forth in the transmission line, all the power will be delivered to the load. So eventually, all power will be delivered to the load. But let's look at how that power, but what we're going to do is let's see how power flows around. So this is the concept of power flow. So let's assume that the phasor voltage phasor is equal to let me just say equal to V0 e to the minus j beta z. So it's only a forward going. We're just at the moment we're just looking at the forward going voltage. And there's a forward going current associated with that forward going voltage. Normally we would put in pluses in here, but I'm not including that for the second because we're just looking at the forward going aspect. So the actual voltage that's related to this phasor, the actual voltage as a function of t and z is that corresponds to this phasor is v cos 0 cos of omega t minus beta z. And the current is I sub s to z is I0 cosine of omega t minus beta z. So if this relationship between the phasor and the actual voltage and current confuse you, go back to our lecture where we're talking about the relationship between the phasors and the actual voltage in those transformations. But these are the phasors. All right. So at a at a as a constant z plane, so at a point z plane, so at a particular point in the transmission line, question is what is the average power that is flowing through there? So that is by definition, the average power is V sub s as a function of t and I sub s as a function of t. And so this is defined as the average power. And just as a reminder, this bracket notation, generally x of t in the bracket, is defined as 1 over the period, is for the power, 0 to t, in the time of the period, x sub t. So it's the average value of what's in the bracket, this bracket notation. Function of t dt. So this is the time average definition. So by bracket of Vs times Is, so this is power, and this means that this bracket means a time average of power in a particular point. Question is what is that? Well, the easy one to always look at is at the load, so at z equal to 0. So at the load, this average value at z equal to 0 is equal to 1 over t. And so that's any period you're measuring around 0 to t. And I'm going to just plug in for these values into the integral. So it just ends up being v0, I0, cos squared omega t, and that is equal to v0, I0 over 2. So that's the average power at z equal to 0. And that's kind of what we expect because we know the RMS voltage is V0 over square root of 2, and RMS current. So this is for a cosine or sine wave, the RMS voltage and current values is I0 over square root of 2. And so it makes sense that the average power would be, oops, would be V0 I0 over 2. All right. Okay. So, and in general, oops, so in, I should write it in. This is, I want to make you guys won't even be able to decipher this. So in general, the Z0 may be complex. The characteristic impedance may be complex. Meaning that it's no longer lossless. The complex one will be um, will will in general not be lossless. So complex Z0, by the way, means that Z0 means phase difference between voltage and current. And also in general, the voltage V0 plus may also be complex. Okay, so anyway, I think if you look at then because of that thing, the P average, the way we would define it, would have to be, sorry, oh man, that's about to sneeze. Would be V0 plus squared over 2 times Z0. The way we would get that is, so amplitude of V0 plus would be amplitude V is equal to IR, so it'd be I0 plus times the characteristic impedance. So I0 would be V0 plus over over Z0. And if I sort of stick that into here, I get this guy. So that's in general, that's the average power sort of going in the positive direction or from left to right in the transmission line. And so for if you look at the reflected wave, for a reflected wave, doing things the same way exactly, but instead of V0 plus, we'll do 0 V0 minus. P average is V0 minus squared over 2 times Z0. And then remembering that gamma sub L is V0 minus over V0 plus, then plugging that into this guy, we end up with Um, let's see, we end up with average power reflected is equal to the reflection coefficient squared, V0 plus squared over 2 times Z0. So let me define P, the incident power, as V0 plus squared over 2Z0, which is this guy. That's the incident power. So then if I plug that into this, I would get the average power reflected. I just copy this. That is equal to gamma sub L squared B incident. So gamma sub L squared is the ratio between the reflected and the incident powers. So basically this means that if you have a unmatched transmission line, meaning a transmission line where there is a reflection coefficient, you'll get a certain amount of power will get reflected compared to what's incident. But again, this will just bounce back and forth and eventually be dissipated in the load. But in the meanwhile, it will cause, unfortunate distortions, etc. But there is a certain amount of power reflected back. Okay, so this is kind of the power flow. So sort of bank this idea again. We're be introducing some concepts and some definitions that we're going to use in a couple of lectures from now on Smith charts. So just kind of remember what we just did here. We're going to come back to it. So the second concept is the concept of impedance flow. And so to look into that, look at the input impedance of the transmission line for some cases of Z sub L. So just as a reminder, so we have the transmission line and has a load and it has a characteristic impedance. The input impedance is defined as going to where the source is, and we usually say this is that the load is at z equal to 0 and the source is at z equal to minus L. So our definition of the input impedance is what does this transmission line look like if we took all of this and pretended like it was just a input impedance right at z equal to minus L. This is just for the purpose of figuring out what a source hooked up to this guy, what it would inject into this transmission line. So again, if you're confused by that, look back on our lecture on in the case of where we looked at the input impedance of the transmission line. So this input impedance of the transmission line is the line impedance at minus L. Okay, so this length of this transmission line is L. And as a reminder, again, we derive this in that input impedance. But for now, all you need to remember is the equation we came up with for this input impedance, which is the characteristic impedance of the transmission line times this sort of complicated equation. It's also complex numerically, which is the load impedance times tangent, plus the J times the characteristic impedance tangent of beta L over Z sub 0 plus J Z sub L tangent of beta L. And beta, as a reminder, is 2 pi over lambda. And so again, this is the input impedance that the source would see. So the source, when it's injecting a voltage into this combination of Z0 characteristic impedance transmission line with a length of L and a load of Z sub L, would see an impedance that looks like Zn when it's injecting a voltage into the transmission line. Okay, so now let's look at this is, an equation that we derived earlier, and you can see that the input impedance, effective input impedance, is not only a function of the load impedance and the characteristic impedance, but also of the length of the transmission line. All right. So for the case of some special cases, so for the case of Z sub L being infinity or open circuit load, so the input impedance, so I'm going to call um, that special case Z open circuit. That's going to be basically, I'm going to plug in ZL is equal to infinity. I'm going to put infinity and infinity in here and look at the ratio, and you end up with minus J Z sub 0 over tangent of beta L. And then similarly for Z sub L is equal to 0, which means short circuit case. I'm going to call that Z short circuit. This equation is going to look like, when I plug in ZL equal to 0, I end up with plus J, plus J Z0 tangent of beta L. And so looking at these two equations, we come up with, or well, somebody did come up with some interesting relationships. Okay. So here's so looking at these two, we come up with interesting observations. The first being that if we don't know, let's say we don't know the characteristics, we don't, so assume Z0 is unknown. So two, we can find Z0 by, so open circuiting the transmission line, open circuit T line load, and measure Z in, sorry, Z in, so that's i.e. Z open circuit. And then the second thing is we can short circuit T-line load and measure Z in. That will be the Z short circuit. And from those two measurements, if you multiply those two measurements together, so we can get the impedance squared, because that'll be impedance squared is, let me just do it this way, is ZSC, oops, times Z open circuit. So that's equal to plus J Z 0 tangent of beta L multiplied by minus J Z0 1 over tangent of beta L. And this cancels out with this. These two give you plus 1. So you end up with the characteristic impedance squared. So basically you can open circuit the transmission line, then you can short circuit the transmission line, and you end up multiplying those two out together, the input impedance of those two together, and you can come up with the characteristic impedance of the transmission line for a case of an unknown transmission line. Okay. All right. So that's one fact again. So bank again, keep banking all this information. Now let's keep looking. So at the case of the short circuit again. So looking more at the short circuit input impedance. So that is short circuit is plus J Z0 tangent of beta L. And then remembering these definitions of beta is omega over the phase velocity. The phase velocity for a lossless transmission line was 1 over square root of LC. And so this combination tells us that beta is omega square root of LC. So plug that in. So let's say we have a short length of transmission line, and let's say the length is, say, delta. So just I'm just calling L delta, and I'm gonna short circuit this guy. So I've actually, like, imagine if you're on a printed circuit board or someplace, you've actually fabricated or printed a short stub of transmission line, and you're shorting the end. Okay, and you're looking at the input impedance into this guy at a length delta. So in that case, for that small section, I'm just going to plug delta in here. So you're going to end up with the short circuit is plus J Z0 tangent of beta delta. So I'm just putting in delta. I'm sticking delta in where L was, because that's just that's the length is delta. And let's say you make, so if delta is very small, we can basically make a something called a small angle. We can use the small angle approximation for the tangent function. And so for very small values of tangent, so for tangent of beta delta, for very small values, this is just approximately equal to beta delta. Okay. The way you can kind of look at that is if you have a tangent, let's see, if you have a so if I have so I'm drawing the say this is x and I'm drawing the tan of x, it's gonna look like this kind of function. So this is pi over 2, this is minus pi over 2. So the small signal approximation basically says that if you really zoom in, zoom in, zoom in, zoom in, right here to very small values, this kind of more or less looks like a straight line. So at very small values around zero, tan of tan of something small is just equals to that same, just like that kind of slope. So this is what the only thing small signal, small angle approximation is saying. So we can use that then to say, plugging it into here, is that the short circuit delta is plus J um, 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 Z sub 0 beta delta. Z0 is for a lossless transmission line, the square root of L over C. Beta from here is omega square root of LC times delta. So looking at what gets canceled here, the C cancels with this C, and we end up with this whole thing equaling to plus J omega L. You get the L's because the square root of L times the square root of L makes it just L and times delta. So if you look at this, this is kind of interesting, is that if what it says is if you have a short stub of transmission line and you short the output, basically you basically end up looking like an inductor. Okay, so if I plot this in terms of impedance, so if I plot beta L, oops, and I plot the Z in for short values of the transmission line, I'm going to look like, so up to about pi over 2, I'm going to look like a purely inductive load. So this is going to look like a pure inductance for up until a certain length of the transmission line. And then if you keep going, and then so this is periodic. So if I look at pi, I'll see the same thing. It'll sort of have this tangent type function. But then what happens is if you when you look at sort of what happens in between, is it'll look like you have sort of a purely capacitive reactance. So this ends up looking like a capacitive reactance. And this, this positive looks like an inductive reactance. So what happens if when you have this short-circuited transmission line, from just the input impedances point of view, you look like you have a pure inductor as your overall load in the case of a short circuit. And then at some point, at some length, you'll look like you have a purely capacitive input impedance. And then that'll at some load again, it'll look like it'll turn into a purely inductive um, reactance. So it'll sort of cycle through looking inductive and looking capacitive depending on the length. So the question is, what do you do with this? Again, just hang on to this till a couple of lectures from now when we get to the Smith chart. This is all build up for that. Okay, so now let's look at, whoops, what happens to the short circuit at as we keep changing beta bell. So, I mean, you can just kind of like read it off this graph, tangent of beta L. Okay, so you can kind of see what happens as you start approaching this length of pi over 2. Your input impedance of a short circuit transmission line looks like it's going to infinity. Okay, so at beta L approaching pi over 2, the input impedance will look like an infinite input impedance. And so what this means that for a lossless transmission line, the reason I'm saying lossless is because for all these calculations, remember we used this equation, which is for a lossless transmission line. And also we use these guys, which is for, impedances, etc., which is for a lossless transmission line. So for that case, um, with short circuit, so short circuit load will look like an open circuit at some T-line length. And that length is del is lambda over 4. And the reason for that is that's for beta L is pi over 2. So we basically are looking for the tangent to go to plus infinity. So if I do 2 pi, beta is 2 pi over lambda times lambda over 4 We want that to be equal to pi over 2. So what did I just do? Yeah. So 2 pi, what am I doing here? So pi over 2, yeah. So that's basically the case. So basically when L is lambda over 4 is when this happens. And this is called a quarter wave transformer. So if you look at a transmission line, if you look at it, so you have a transmission line with a with a short circuit load. So this is a short circuit up to a length of lambda over 4. You look like your, your some inductive value. Then at some that lambda over 4, you will look like, an open circuit. And then you'll keep that whole thing will keep going. So as you add more length to it, at some at some length, lambda over 4, it'll look like a short circuit, and then so on and so forth, and it'll just keep going like that. So it's a very periodic, um, um, basically, the input impedance looks like a periodic function of the load. So for a Zn, for a short circuit, load is periodic with changing length with a period of, so if I call this L, the length, the periodic length is lambda over 2. Okay, so again, um, bank this for the case of, this will be important. So again, important for the Smith chart. Smith chart lectures coming up. Let's see. I guess that's kind of what I all I wanted to say about that for this lecture. Again, some background stuff that's going to be useful for our Smith chart lectures.